a problem like this, if you're asked for an electron configuration with a lot of electrons, the first thing I would look for is, are the n values listed in increasing order? And what I mean by that, remember the number in front is the n. And notice here how 4 is first, then 5, then 6. This is not listed as a true electron filling order, which is what Aufbau is all about. But this will be really helpful when we start making the ions, when we make positive or negative ions. And again, you'll see these listed both ways, and I'm just throwing them up here just to give you a heads up. So this is not listed in the way that the electrons are going in, but this would be helpful when the electrons are coming out. If you look at the Aufbau diagram, which is why you should have, if you can get one of these around you, it's really helpful. 6s is at the end of this little arrow right here. It's kind of hard to see. But after 6s, 4f gets filled in next, then 5d, and then 6p. So really, if this was an electron filling order, it would say xenon 6s2 would be right there, 4f14, 5d10, and 6p2 on the outside. So my first little hint here is just if it's listed with bigger n, like 4 to 5 to 6, then probably it's the way that will help you when you take electrons out, but it isn't the way that you'd probably figure it out using an Aufbau diagram, et cetera, et cetera. That being said, this problem is not too bad, because the last ones in will be the first ones out, which we'll talk about in a little bit. 6p2 is the electron configuration for this neutral element. And you know it's past xenon, all right? So what I would do if I was doing this is I'd first start off here with xenon, all right, which is the end of the 5 p's. Then 6s2 would be cesium and barium. This is the first time we've seen one of the F blocks, but it's no problem. An interesting thing about F blocks, if you count it up, there's actually 15 elements right here. For a long story short, chemists can't decide if the 6d electron is first followed by the 5f14, or if it's 4f14, excuse me, followed by 6d. We don't need to worry about that. Just realize that the F's and the D's are all going to get filled in, and we're going to get over here to mercury, which is 6 minus 1, 5d. Then over here is, thanks for playing. What are we looking for? 6p2, sorry. Anyway, so 6p1 would be thallium. And again, everything in this column is a p1, all right? So like earlier, aluminum was a 3p1, all right? And in this case, then 6p2, 6 from here, p block, second element in that, it should be lead, all right? So there's many different ways that you could do this kind of problem, but that's one way. Another way that you could absolutely do this problem, xenon's number 54. So 54 plus 14 plus 10 plus 2 plus 2, it should also equal 82, which is another way to find out that it's lead. So hopefully you're seeing there's more than one ways to do this, and any way you do it is fine. Be careful of the order, all right? And that'll be helpful to you sometimes and also frustrating to you when you're learning it, but they're listed both ways. Any questions? Okay, and again, JQ isn't a real element, stuff like that to see. Okay. This is the first example we've seen of an ion. And remember, an ion is just an atom with an excess or a minimal amount of electrons in it. This is an anion because it has extra electrons in it. And remember that P minus 3 means 3 extra electrons. So see if you can figure out which of these would represent the electron configuration for phosphide, the P minus 3 ion. So on a problem like this, what I would do is I would first find the neutral electron configuration for phosphorus. All right, the lower left-hand number is the atomic number, which means 15 protons, which means for this problem, neutral phosphorus would have 15 electrons. Now, neon represents how many electrons? 10. Well done. And the way to figure that out, look at the atomic number on there. It's number 10. So this is 10 of my 15 electrons. The next two go in the 3s orbital, because again, we filled in the 2p to get up to neon, so 3s2. And then the last 3 electrons for neutral phosphorus would be 3p3. So you could write this neutral phosphorus as neon 3s2 3p3. Now, I want to write this in orbital box notation because I can introduce some ideas here that are important. 3s2 means a spin up and a spin down. So that would be the way I would write 3s2 for phosphorus. And then 3p3, like we talked about in lecture, you want to put 1 electron per box whenever possible. This is called Hund's rule. I could have written phosphorus as a spin up and a spin down in the first box, and then like an empty box right there. But Hund's rule says 1 electron per box. There's a little bit of energy required to have an up and a down in the same orbital. And so to avoid that cost, we put them in individual orbitals first. And I use the idea that this is like if you live in a house and you have to live with a brother or sister, it's okay, but it's nicer to have your own room because you can have your own music or posters or whatever. Stupid, but anyway, that's what electrons would do too. So these are both ways to represent neutral phosphorus. Is that cool? Any questions on that? Okay. When you have an anion, you're just adding the number of negative charges, negative electrons. So we're going to add 3 electrons to phosphorus here. And adding electrons isn't too bad. Remember that p's can hold up to 6. So that would change this 3p3 to a 3p6, which we're going to see as the answer. On the orbital box, you can see where that happens. Now we're going to start pairing up. To go from 3p to 4s is a pretty big energy jump, and you don't usually want to do that. So this is now when we will start filling in the orbital box, those orbitals. So there'll be a spin up and a spin down. It's going to be neon 3s2 3p6. You can absolutely write that as argon in square brackets if you want. I was trying to make it more interesting as a teacher, okay, but hopefully you get the idea. Any questions on that? So when you're making an anion, a negative ion, the electrons just go in the first available slot, all right? Like you would, instead of having phosphorus, you'd figure out the electron configuration of argon, all right? That's kind of what this is all about. If you have to guess on these, I mean, most of the time the anions and cations will want to be like the noble gases. The transition metals and those guys are different, but the main group metals and non-metals, they generally want to be like a noble gas. Questions? Okay, here's a problem you might see. Which ion corresponds to the following electron configuration? Now, unlike the last problem, these are all cations, positively charged ions. If you're taking away an electron, all right, I'm going to go back to neutral phosphorus here. When you're taking away an electron or electrons, this is now where you want to start thinking about highest n and highest n plus L. When you take away electrons, you want to take away from the highest n first. So like phosphorus has 1s2, 2s2, 2p6, but those all have n's of 1s and 2s, and those are lower than n equals 3. So highest n means we're going to take it away from n equals 3 first. But there's a tie here, 3s and 3p both have n equals 3. And if there's a tie, then you take it away from highest n plus L. And what that means is you take it away from the last electrons you put in. So phosphorus 3 plus you would take away all of these electrons, but leave these ones here, because 3p higher n plus L than 3s. So in this problem, notice that there's an empty 4s orbital, all right? Higher n equals 4, then n equals 3. So when these kind right here, make sure you take away from 4s first, then take away from 3d. Anyway, play with this, see what you find. We'll talk about it here in a little bit, and I'll give some more examples of what's happening. Okay. Does it seem possible that with 3d and 4s orbitals you would have a lithium ion? No, good. Lithium is number 3. It's a 2s orbital on the outside, and here we're talking about 4s's and 3d's, so there's no way it's going to be a lithium ion. It doesn't have enough electrons, all right? If you think about it and you look at the periodic table, rhodium is also not a possibility. Rhodium is number 45, and rhodium is part of the 5 minus 1 4d orbital subset. So rhodium would have a 3d10 configuration, but it's going to have a 4d somewhere or another. This is not a possibility. Rhodium has too many electrons, all right? The 3d set is the transition metals, the first row of transition metals. So iron, cobalt, and nickel absolutely do kind of fall in there. Now, when you have a problem like that, what I try and think about the neutral atom, and if you took away this many electrons, would it look like this part right here? So, like I was talking about, all these crazy transition metals, the 4s would get filled in first, and the 3d after that. That's because back to the n plus L rule, after you fill in 3p, 4s gets filled in, and then 3d. All right, so the 4s gets filled in first, and then 3d after that. But when you're taking away electrons, which is what it is here, again, the rules, highest n first, and if there's a tie, highest n plus L. Highest n means that 4s is going to come out before the 3ds, and that's what makes these things kind of interesting. The transition metals have very similar properties because the ions, which are what people deal with most of the time, the 4s electrons are all gone. So it's basically the electron behavior of 3d electrons. But anyway, I digress. How I do these problems, all right, is I think about what the neutral atom would look like, which would basically be all of these electrons plus these two right here. So if this thing was neutral and it was 4s2, then there'd be 1, 2, 3, 4, 5, 6, 7 3d electrons. So if you start here with scandium, scandium would be a 3d1, 3d2, 3d3 for vanadium, 4, 5, 6, 7. Cobalt would have a 4s2, 3d7. And cobalt 2 plus, you'd take away these 2 electrons, but you'd still have 7 there. So cobalt here, cobalt 2 plus, would have this configuration. Neutral cobalt, 4s2, 3d7. But when you take away electrons, always take it from the highest n, which means 4s comes out first. But cobalt 2 plus would still have the 3d7 electrons. You can see here on nickel 2 plus would be 3d8, iron plus 3. You take away 2 electrons from 4s and a 3d electron to make it 3d5. Any questions? Again, if you see problems like this, what I often will do is I start with the neutral atom and then I take away 2 electrons and just see if it looks like this, all right? And that's usually a pretty good way to figure these things out. Questions? All right. Magnetism is also an important part of these. Magnetism means that they have just as many up electrons as down electrons. So if you have a 4s2, that would have an up and a down. And if all the ups have a down, then it's referred to as diamagnetic. However, if you have even one unpaired electron, like a 3d1 in scandium, that would be enough to make it paramagnetic. So scandium would be paramagnetic and calcium would be diamagnetic. See if one of these are diamagnetic, and punchline, one of them is, all right? But see if you can see which one of these will be the diamagnetic ion, where you have just as many up electrons as you have down electrons. here on the chalkboard, I have an argon 4s2 3d2 electron configuration. What neutral atom does this represent? Titanium. Well done. So titanium. Now, if you're still like, what the? All right, I understand. 4s2 is potassium and calcium. And then scandium would be the beginning of the 3D, 4 minus 1, 3D, 3D1. Titanium would be 3D2, 3D3 vanadium, 3D4 chromium, etc., etc. So if this is an argon 4s2, 3D2, this would be titanium. If you're taking away electrons from a transition metal, the highest N always goes first. So even though it's tempting for titanium, you want to take these away and make it like diamagnetic. What actually happens when you make titanium plus 2 is that the 4s electrons go away and you end up with a 3d2 configuration. And because each electron goes in its own orbital first, that means titanium 2 plus is definitely paramagnetic. If you could take away these electrons, then it would make it diamagnetic, all right? Because 4s2 would be 1 up and 1 down. But highest N comes out before lower N, which means 4s before 3d. So titanium 2 plus is paramagnetic. Any questions on that? Is that cool? All right. Vanadium would be a 3d3, and chromium would be a 3d4. But all of them, when you lose 2 electrons, they come from the 4s first. So all titanium, vanadium, and chromium, all paramagnetic. Now, magnesium right there, neutral magnesium has a 3s2. And making it magnesium 2 plus, you take away 2 electrons from the highest N, which is 3, minus 1, minus 2, it's going to go back to neon. And all the noble gases are diamagnetic. So if you see anything that's a main group metal with an ion, it's probably going to be the diamagnetic one. And in this case, that's definitely the case. Magnesium 2 plus is diamagnetic. All the noble gases have diamagnetic configurations. I think it was Wes last Monday said that he was looking for like even and odd number of electrons, which was really cool. All of the noble gases are diamagnetic. And also things at the end of a period, so like these guys at the end of the Ds, and these guys at the end of the S's, those will always be diamagnetic. But when it comes to the ions, then usually it's the noble gas configuration you're looking for and stuff to see. Any questions on that? If you have to guess, most transition metals and lanthanides and actinides are paramagnetic. They'll have like 1 or more unpaired electrons. So like for chromium 2 plus, it would have 4 unpaired electrons, which is pretty paramagnetic. So, and if you have to guess in general, neutral, ion, whatever, there's a lot more paramagnetic things out there than diamagnetic things. But the diamagnetic ones are important. We're around them a lot. So, cool. Questions? Any of that? Nickel plus 2. Which one of those is the correct electron configuration? And remember, highest N out first. Let's see if you can figure it out. All right, so this is nickel. Nickel is number 28 right there. Which noble gas will we use in the electron configuration for nickel? Argon, that's right. So you start with nickel and you go backwards, don't go forwards. Backwards to the nearest noble gas, and number 18 is argon. So it's going to be C or A, but it won't be krypton or helium, all right, which is, helium's kind of silly. It's going to be one of the argons. Now, when you do the configuration for neutral nickel, it would be argon, 4s2, 3d8. And again, neutral nickel, start with argon, 4s2 gets you to calcium, and then nickel right there, 1 for scandium, 2 for titanium, 3, 4, 5, 6, 7, 8. So neutral nickel would have a 3d8. But obviously this is not neutral nickel, this is nickel plus 2. So the question is, do we take electrons from the 4s to give it this, thanks for playing, to give it this configuration, or do we take the electrons from the 3d8 to give it this configuration? Which one of those do we take it from first? 4s, that's right. Highest n out first before lower n. So we would take those 2 electrons out to make it nickel plus 2. The configuration should be argon 3d8. All right, highest n out first. Yeah.
Wait, so why is it 3D? What? Because isn't it in row 4?
Cool. The D's are this number minus 1. That's a cool question. Yeah. So like scantium is the beginning of the D's, but it's 4 minus 1, 3. Okay? And I'm glad you brought this up. And down here, when you get to the F's, it's this number minus 2. So just remember, yeah, D's are the number minus 1, and the F's are the number minus 2. Good. The S's and the P's, you can use them direct. It's just the other ones you have to configure. Good, great question. Other questions? 10 plus 2 is when we saw 10, neutral 10 earlier. See if you can figure out which electronic configuration would be appropriate for the 10 plus 2 ion. So 10, if you look it up on the periodic table, it's number 50. Krypton, if you go backwards, is the nearest noble gas. Then, just like Kane brought up earlier, which was a really cool question, 5s2 would get you from rubidium to cerium, or strontium. But then yttrium is another D block. So we go 5 minus 1 or 4. Yttrium begins the 4D orbitals. And it's totally filled up, so we have a 4D10. But then on the far right, we've got the 5 again for the 5p block. It would be 5p2. So 10, neutral 10, krypton 5s2, 4d10, 5p2. Any questions on that? Okay, now this is 10 positive 2, so we need to take away 2 electrons. So remember then that the rule is highest n first, and if there's a tie, highest n plus L. Well, in this problem, we have 2 n equals 5 systems, and that's bigger n than 4, so we're not going to do anything with the 4. But we do have a tie, all right, 5s or 5p. So highest n plus L, if there's a tie, means last ones in are the first ones out. You didn't do that back here with like titanium 2 plus or whatever, because highest n comes out before highest n plus L. But in this case, we do. So in this case, we'll just take out the 5p2. That's higher n plus L, i.e. it was filled in after the other ones. So it would be 5s2, 4d10. Notice how these configurations are listed sometimes. Like 4d10 is on the outside, right? You'll see some kind of screwy configurations sometimes for things. But as long as you know how to fill them in and take them out, you're good to go. Any questions? All right. So atomic or periodic properties is kind of the periodic trends is the last big part of this section. And these trends are a little cheesy, in my opinion, but like we talked about in lectures, sometimes people will ask me the most random questions at the random times. And I may not have my phone, or I may not be able to look up something fast enough. So periodic trends make me as a PhD look cool, right? And now you can be just as cool as I am, which I know you're just dying to do. But anyway, there's different types of trends. This has to do with size, radius, all right? And when it comes to size, think of the periodic table as basically a rectangle. Hydrogen would be in the upper left, helium in the upper right, and francium roughly lower left, and radon roughly lower right. Anything to do with size gets bigger as you go left and down. And it can be the ion size or radius, it can be neutral atoms like this one is, anything. But size generally gets bigger as you go left and down. So for these 4 elements, what I would do, try and figure out which one is more left and down on the periodic table. See if you can do that, and that should be the largest radius of those different atoms up there. So again, look for the one of those 4, which is most left and down on the periodic table. Okay, so in this problem, we have sodium, aluminum, boron, and carbon. Those are the 4 things we're thinking about. And left and down literally means going left and down on the periodic table. So boron is more left of carbon, aluminum is more down than boron. But as you can probably see, sodium is the most left and down on the periodic table. So we would predict that the one with the largest atomic radius would be sodium. Now again, these periodic trends are rough. There are exceptions, like we talked about last week, Monday, but overall, they're not too bad, especially the ones for size, all right? So you literally just look at the periodic table, left and down. JQ is not an element, so don't use that one. But that's literally all there is to it. And again, if you're publishing, you should definitely take the time to look up these values to make sure the periodic trends are right, but more often than not, they're pretty good. Any questions on that? Okay. This one is all about ions, all right? And again, largest radius means largest size. So anything to do with size, most left and down. See if you can figure out which one of those would have the largest radius. And again, left and down. So if you look at the periodic table, argon, Cl, S, and P are all right there next to each other. And again, the punchline, left and down. So knowing just that, which one of these four is most left and down? Phosphorus, absolutely. So this periodic trend works pretty well. Now, these are anions. And we talked about how electrons and protons have kind of a weird play to them. Like the anions are always bigger than the atoms they came from, because as you have extra electrons relative to the parent protons, the electrons tend to wander a little bit. Cations, positive ions, are smaller than the atoms they came from, because now you have the same number of protons but fewer electrons, so they get pulled in more. So phosphide has the fewest number of protons here. We're basically going 15, 16, 17, 18. And all of these have 18 electrons. So phosphorus has the most children electron relative to proton parents. It tends to be bigger. The things tend to get away from it. When you're doing ion sizes, you can only compare anions to anions or cations to cations. You can't really compare phosphide to the sodium plus 1 ion, all right? But that being said, and knowing that I'm a good guy and I'm not going to ask you weird questions like that, if they're all anions and neutral, then the one with the fewest protons should be the biggest one in this one. Any questions on that? Okay. Now, the other periodic trends that we talked about, let me draw a new periodic table up here. Electron affinity is one of them. Ionization energy is one of them. And I am going to throw up here, although I'm not going to ask you questions about it right now, something called electronegativity, which is something in Chem 222 is going to help us out a lot if you're taking it there. Now, just like before, hydrogen, upper left, helium, upper right, radon, lower right, francium, lower left. Well, the ones for size increase left and down. These guys all increase up and to the right. Now, sometimes the noble gases aren't included, but again, I'm not going to ask you questions with noble gases necessarily. But what I'd like you to do here is figure out which of these has the largest electron affinity. All right, the biggest electron affinity. And again, the punchline here, up and to the right.
These are intentionally the same elements as before. And again, as before, we're going to think about how electron affinity works with these. And again, the punchline, up and to the right. So in the last one, sodium was the biggest size, but here we're after electron affinity. So we want up and to the right. So more to the right than sodium is aluminum, but more up is boron, and the most up and to the right is carbon. So we would say for this problem that carbon has the highest electron affinity. Now, these guys are very troublesome. Their Pyrrhic trends honestly don't work as well. However, overall, if you don't have Google or access to a computer or someone sells you in the restroom, which happened to be one time, I was like, really, dude, right now? But anyway, that's a long story. Anyway, up and to the right is the way to think about which one is the biggest. Now, electron affinity is weird because it's an exothermic number usually. It means most negative. You don't even have to worry about that. Just for us in this problem, in this class, up and to the right. And that works for electron affinity, ionization energy, and also something called electronegativity, which we'll look at next term. And another point, I always get asked this too. In a problem like this, what if you had boron versus silicon? Which one is more up and to the right? And the problem with that, boron is more up, but silicon is more right, okay? I won't ask you those kind of questions because the trends are so lame. With size, generally down is more important than left, all right? So if it was size and it was left and down, like you could have, I don't know, calcium and strontium or something like that. Generally, the down one will be bigger. With these guys, though, they're all over the place, and it would be harder even for me to tell which would be bigger. So just realize, I'm not going to ask you ones where, one is more down and one is more up or something like that. They'll be very obvious. Is that cool? Good. Last question. This is ionization energy, and I want you to put them in order of increasing first ionization energy. Now, ionization energy is also up and to the right. So what that means, if it's increasing, you want the most left and down first, and the most up and to the right last. You don't need Google, although Google would tell you for sure. So see if you can figure out what the order of these are. And again, up and to the right is how you find them bigger. Ionization energy is the energy required to remove an electron. First ionization energy would be the first electron to be removed. Second ionization energy would be second electron removed, etc., etc. Do metals lose electrons easier or harder than nonmetals? Which ones are positive, metals or nonmetals? Metals, okay. So metals lose electrons easier than nonmetals. That's why in all these periodic trends, you start with the lower left. This is the heavy metal area down here. And as you get more and more to the right, it gets harder and harder for the electrons to be removed. It's relatively easy down here. It's much harder up here. All right, so that's kind of the theory that's going on. So of these different elements then, magnesium is certainly the metal, all right? So magnesium should be the easiest to remove. Now, C, N, and F, C, N, and F, magnesium down here, up and to the right for ionization energy, magnesium over here, up and to the right, carbon, nitrogen, fluorine on the outside. It should be answer A, okay? So you don't need Google, you can use this trend, and it works more often than it doesn't, even though these are lamer, honestly, in my opinion, than size, but I digress. Any questions on that? So the sizes will be really cool. We're going to do some stuff with sizes of atoms later in the different chemistry courses, and knowing they get bigger left and down can be really helpful. These guys are kind of nice to know. It's basically rationalizing why the metals are positive and the non-metals are generally negative. Metals are easier to lose their electrons. On the other hand, with non-metals, if they gain electrons, the electron affinity, you actually get some energy out. So it's justifying why the positives and negatives form, like why the metals give the non-metals their electrons, stuff like that. But that's it. Woohoo! All right, and with that kind of thing. So anyway, very cool. So Wednesday, once again, we'll look at problem set number 6, bring that, and definitely bring a printed copy of the hydrogen spectrum lab. You'll finish that before you leave for lab. If you want to look at the lab right now, you have a lot of the skills to knock some of the problems out. On the other hand, you just want to come and do it, that's cool. Bring a calculator on Wednesday. We'll do some calculator work. Any questions? Have a great day. Thank you for being here.